And please tell me if I get too low on the blackboard that the people in the back don't see anything anymore. And as well as the title of the talk says, it's about T-structures. T-structures have been very useful in geometry, in representation theory, and other fields. And traditionally, they were mostly used in categories, at least in geometry, were mostly used in categories of constructible sheaves. But slightly more recently, lots of T-structures on derived categories of coherent sheaves showed up. So the prototypical example maybe are the various categories of perverse coherent sheaves. Coherent T-structures. And the one I'm going to use, or the one that's closest to what I'm going to talk about, is the one given by Bezrukavnikov, Arinkin, and maybe based on Delin, that's on the equivariant derived category of some variety. And it turns out that these T-structures are particularly nice if all orbits have the same parity. So nice if all orbits have, say, even or odd dimension. So an example where this has been classically studied is the nilpotent cone. It's well known the nilpotent cone has all even-dimensional g-orbits inside the Lie algebra. Another example where this comes up is if you take some orbit closure in the affine Grassmannian, then it's also well known that that has even-dimensional g of O orbits. So by that I mean the orbit closure in the affine Grassmannian indexed by some dominant weight lambda. So in all of these you have nice, or the equivariant derived categories, you have nice T-structures that have been studied by various people to various effects. But of course these spaces don't live in a vacuum. There are other spaces that are closely associated to this. So for example, for the nilpotent cone, we all know and love the Springer resolution. And on the Springer resolution, you suddenly don't have all even-dimensional orbits anymore. So you don't expect to get a nice T-structure just from perverse coherent sheaves. Similarly, on here, what you can do is you can take some convolution varieties. There are article lambda with an underscore, so that's we take some and convolve them, which is a map down to sum of lambda I. And again, here you have even-dimensional orbits. Here you have all kinds of orbits. And sort of a nutshell question to ask, the other way around, is whether there are some useful, nice T-structures on the derived categories upstairs that map down to the T-structures downstairs. So natural question that we are going to study now, are there T-structures here? Here, such that, so that they don't float in a vacuum, such that pi star or m star is T exact. And for this category, the answer has been given. So the answer for the derived category of the bounded derived category of the Springer resolution is called exotic sheaves, and have been defined by originally as Bezrukavnikov and then various collaborators. I'm not going to write Bezrukavnikov all the time. B dot will stand for Bezrukavnikov because he did a lot of work around these things. So if you want to, say, define some t-structures in here, maybe a good place to start is trying to understand what Bezrukavnikov and other people did here. So let me give you some definitions of exotic sheaves, and we'll see whether we can generalize something from these definitions. The first one that I want to mention, even though it's not historically the first one, there is an equivalence of this derived category with some other derived category, antispherical perverse sheaves on the affine Grassmannian of the dual. Whatever that is, it's not important what that is for us now. That was given by Akipov and Bezrukavnikov. And this thing has a natural t-structure, even though I'm not telling you what it is. This has a natural perverse t-structure. And that exactly corresponds to the exotic t-structure here. Okay, very nice, very deep result, but it doesn't really generalize. If you have some other things than the Springer resolution here, then where would you cook up something like this? Where does it come from? So no idea. That doesn't really help us for generalization. Another definition that was probably the original one by Bezrukavnikov is find some exceptional set in here. Find exceptional sequence. Then do something to it called mutation, which is essentially using a different order for the exceptional sequence. And then to an exceptional sequence, you can always associate a t-structure. So that's a more general approach. Finding exceptional sequences, there's a whole business around that. But it's a hard thing. So if you look at some variety like this, you wouldn't know whether there's an exceptional sequence or not. There might not be one in general. So it's also not that trivial to generalize. And then the second part, mutation, has something to do the way he did it with representation theory. Again, doesn't really generalize, so you don't know what to do in general. So these two things didn't work out so far. So where this actually starts from, the more useful thing is in a paper by Bezrukavnikov and Mirkovic. And what they did, well, you have another tool that where t-structures usually come from is find some tilting bundle. But the specific thing that they do is they don't find a tilting bundle immediately on here. They find a tilting bundle on the Grothendieck-Springer resolution. So they find a tilting bundle on G tilde instead of N tilde. And then you have an equivalence of dB N tilde G. Let's call this tilting bundle something. Let's say A with dB and A mod finally generated equivariant, and A restricted to, sorry, this is very small now. So the restriction of A to the Springer resolution, take endomorphisms of that, then you always get, that's basically one of the defining things of a tilting bundle is you get an equivalence of categories with modules over the endomorphism of the bundle and the original category. And now you can take some natural t-structure here. So this turns out to have a natural perverse t-structure, which again corresponds to the exotic one. So from a point of view of generalization, you can always try to find a tilting bundle. But again, that's a very hard thing. And the way, well, the construction does generalize somewhat, but the proof that it's a tilting bundle in that paper goes somewhere through modular representation theory, so it's not obvious why you would have some proof like that in some generality. But nevertheless, there's an important hint for generalization here, and that is they construct the tilting bundle on G tilde, not on N tilde. So I'll write this down here. Hints that we get from those various definitions. The first thing is look for analogs of G tilde. And the reason why this is important will come up later, but essentially is that you have just more space to play with if you look at a bigger variety. And the final definition that's in the same paper is not a construction, but just an axiomatic definition. Which are three axioms. The first thing is you want, well, what I said earlier, pi star should be T exact. The second thing is a bit mysterious. So they proved, or Bezrukavnikov and Mirkovic proved, that there is an action of the affine weight group on this derived category. So this is, I think, Bezrukavnikov and Mirkovic. So that's again a deep theorem. It's not trivial where this comes from. But anyway, the condition then is that if you take the submonoid generated by the images of the simple reflections, so the submonoid, not the subgroup. So all the things you can write in positive powers of this. The action of this should be right exact. And finally, there's a third condition that's technical, plus, I don't know, I'll say normalization. That it's a bit more involved to formulate. So again, it's not clear why this affine weight group action acts on this. I mean, you can write down generators, but again, how do you generalize this? But nevertheless, that's sort of the starting point that we took off. The hint that we got from this is look for sources of affine weight group action, for sources of weight group actions. So look for BF actions. All right, and as I guess the title of the talk suggests, our weight group actions will come from categorical actions. And maybe as my co-author suggests. So any questions so far, motivation-wise? So let me, since I'm the first person here to talk about this, let me give you a quick rundown of what I mean by categorical or geometric action. So part 2 will be categorical, or what we want to do is more geometric, and I'll specialize to quantum affine GLM. So again, these things have been studied by a variety of people. I think originally this kind of setup was suggested by Rouquier and Zhang and Rouquier. Did I write this correctly? Kovanov-Lada had some formalism. Rouquier alone. And unsurprisingly, the thing we worked with was the setup brought forth by Cautis and Kamnitzer. But I won't go into any deep detail in what this involves, because the result I want to talk about is more combinatorical. So I just want to give you an overview what the combinatorics of such a thing should be. And some notation. I'll have the weight lattice of GLN. I will identify with Z to the n in such a way that the roots alpha I are given by 0, 0, minus 1 in the ith position, 1 and zeros again. And the affine root I'll specify to be 1 bunch of zeros minus 1. So I'll look at somewhat specific GLN head actions. And now in a normal representation, you know it splits up into weight spaces. So in a categorical way, we have to split up into weight categories. So I'll have categories that I write k of k. So if I write weights in this indexing way, I'll always denote them with a k. And since everything is geometric, I'll immediately specify to some coherent derived category of some space, some variety x of k, potentially equivariant. So everything I can do equivariant or not, and you'll get results either way. And I said UQ GLN head, so there's some quantum thing, so there should be some grading somewhere, plus grading. But in the interest of you not having to watch me trying to figure out gradings here, I'll usually suppress the grading. Just be aware that if one actually wants to prove something, then gradings are very useful because it lets you split things up. But they're kind of annoying to write down on a blackboard, so let's skip that. Now in a classical representation between the weight spaces, you have operations EI and FI coming from SL2 triples. You have the same thing here. Instead, now there will be functors. And I'll again specify them to the geometric setup, so I'll have Fourier Mouquet functors. Mouquet functors. Going from one category to the category k plus a root. And I notice I'm rather low on the blackboard, so I have EI going up the root plus alpha I, Fi going down. And these things then have to specify, satisfy a bunch of combinatorical requirements. And I'll give you an example in a minute. So what do I want? The first thing is that E and Fi should be somewhat related, and specifically they should be adjoint. So I want EI, the right adjoint, and the left adjoint of EI should be essentially Fi, but I said I suppress grading, so up to a specified grading shift. then I need commutator relations. So I have EI, FI should be the same as doing it the other order. But again, as in usual representation theory, that is not true on the nose. You'll get a bunch of identities. So plus big direct sum of, you write it this way, it. And I'll have alpha I k many. So again, I'm suppressing gradings. What I mean by this is essentially there should be in various grading shifts all these identities. And if this is a negative number, then this should be on the other side. Because on a categorical level, I can only add things, I can never subtract things. So if I would have to subtract something in the usual setting, then I would have to put it on the other side. So there's a symmetric thing if the index is negative. If I is not j, then as usual EI and Fj should commute. Fj EI. And finally, I want to talk about finite stuff, so I have some finiteness conditions. So if I actually want to set up things like this, then of course just specifying a bunch of relations like this is not enough. As everyone knows, on a categorical level, we have to deal with higher category structures, so this should actually be a 2-category. There should be some additional data to make everything work out nicely. But in the interest of actually getting to some results, I'm not going to tell you the exact lists of axioms. Maybe just pointing out one thing. These things are enough to also get something like categorified Serre relations. So you get more relations out of just relatively few ones. OK, I promised some examples that might be more interesting than me going over a bunch of axioms. Let's do this in the middle, it takes a lot of space. So how could we write down something like this? I need to fix some numbers m and n, positive integers. So the categories should be derived categories of some spaces, so I need to give you some spaces. And sort of the example that we mostly looked up at is spaces y of k, which are given by a flag with jumping, so with dimension jumps indexed by k. So we'll start in Laurent polynomials to the m, called L0, then L1, so various spaces up to Ln inside, this should be polynomials inside Laurent polynomials. So what do I want? I want to have the k giving the dimension jump. So I want to have the dimension of Li mod Li minus 1 to be equal to ki.
What do you actually mean? Laurent polynomials, not rational functions.
Rational functions, sorry. I wrote the right thing. I wrote what I didn't say the right, sorry. Okay. Rational functions. Or, I mean, you could write power series and Laurent series. I guess got mixed up in my, yeah, I wrote the right thing. And we sort of want to model, as an example, we want to get the nilpotent cone. So we want to have Z as a a nilpotent operator, so we want set Li to be contained in Li minus 1. So I'll usually write this as given the jumps up here, so this is k1, this is dimension jump k2, and so far until kn, and we'll have z has to act like this. So for example, the most familiar of these things, if is m is equal to n is equal to n, and then I have y 1, 1, 1, so m times 1. So I have a full flag, so I have a flag with jumps 1, and I have an operator that goes down, so it's a nilpotent operator. So this will be some kind of compactification of the Springer resolution. The opposite extreme, if I have a jump by big N or little n, it's the same, and nothing else, then everything collapses. Then here I just I have to give one space that has to be killed by Z, so there's no choice at all, so this will be just a point. And in between I have various sort of partial Springer they're not Springer resolutions, but I don't know what the word is, partial flags plus a nilpotent operator that stabilizes it. Let me write this over here. More generally, to tie back into the examples I gave at the beginning, if I write lambda equal to omega k1 up to omega kn, where the omega I are the fundamental weights of SLN, and then one can check that y k1 up to kn is the same as that convolution variety I had at the beginning. So these examples in particular include convolution varieties where I only allow fundamental weights. So these are sort of the two basic examples that are included in this kind of construction. So you get all kinds of partial convolution varieties, or various length convolution varieties. Now I used up the big board in the middle. How bad is this to read right now? If I write on here.
If you write,
Try to write visible. Maybe if I use yellow. So I've given you some spaces, and the categories K will then be the derived categories or equivalent derived categories of these things. How do I define, say, E1 in this setup? And let me just specify to n equals to 2 for simplicity. So what do I have? I have some variety yk. Is this readable? That consists of a flag L0 inside L1 inside L2 with K1, K2, and Z going down. Then E1, what will it do? It will go to the derived category of yk plus alpha 1. So that has a similar form, say L0 prime inside L1 prime inside L2 prime. And now alpha 1 decreases K1 and increases K2. So that jump decreases and that jump increases. And now E is just defined by finding some kind of head for this diagram. So what can we do? We can look at a flag flags L0, which should be the same as L0 prime. they're just polynomials anyway. Then the next smallest thing on the board here is L1 prime. That's just k1 minus 1 dimensions bigger. Then the next smallest thing on the board is L1. That's 1 dimension bigger. And then that sits either in L2 or L2 prime. So L2, which should be the same as L2 prime, with a jump of k2. And now, well, Z should map L2 prime into L1 prime, so it should map like this. And it should map L1 into L0, so it should map like this. And then I have canonical maps down here and down here by just projecting on either the non-primes or the primed ones. And E1 will just be pole push along this diagram, maybe tensor with some vector bundle. And some line bundle, actually. So there are fairly obvious ways to define these EIs. The only thing where you have to think a bit is for E0. That's where you can't just write down a diagram like this. That's I guess the harder part, which is easiest to describe in some kind of loop presentation instead of the kind of catch-moody presentation that I gave earlier. So what has this all to do with the two hints that are now erased? Let's look at the first hint. The first hint, we should look at some analog of the Grothendieck-Springer resolution. Here I gave you some analogs of the Springer resolution. Well, making it an analog of the Grothendieck-Springer resolution is not too hard. Make this example 2 and just remove that -1 here. Now we have a flag that's stabilized by Z. So it's a flag plus an operator, so it will be some generalization of the Grothendieck-Springer resolution instead of the Springer resolution. And for various choices of Ki, I'll have compactifications of various partial Grothendieck-Springer resolutions. In particular, at the outermost level where the flag collapses to just the choice of a single vector space, I just have a compactification of the actual Lie group. And of course, I could write this just as a usual flag plus an operator, whereas the various different Grothendieck-Springer resolutions, then I wouldn't get compactifications, I would get them on the nose. And this then, of course, is not correct anymore. So you don't have, I don't know what these spaces would look like. And then the EIs and FIs you can define in a very similar way to the example 1. All right, and now where does the second hint come in? It's a general fact that if you have these kind of categorical actions, you can get braid group actions out of them.
Sorry, just a comment.
Yeah.
I mean, this thing has a description as using valence and Dirichlet photographs. That generalizes your description.
Sure, but I don't know what to exactly write down here. What the exact words for these?
Just write BD as a subscript.
Okay. So, and also notation-wise, I'll call them fat-wise. So. What we had before, K is BD, something like this. Okay, yeah, they have descriptions, but, well, no buts. And there's a whole paper, or a bunch of papers by Joel, for example, discussing these things. Is better. So where do the braid group actions come in now? So they should act on the direct sum of all these categories. Remember, I had some, well, still here I have some finiteness conditions. Fine. Whatever. So this will be some finite sum. And how should the braid group act? It should have generators Ti going from the category indexed by k to the category indexed by what I'll write as Sik, so this will be switch ki and ki plus 1. And in the t equals naught case, I'll switch the last and the first index. So how could one get such functors? Again, somewhat motivated by usual representation theory. So let me draw a diagram. 1, 2, 3. 1, 2, 3. So if, say, here is the category indexed by k, then the category indexed by Sik would be here. So this is the SL2 version, I suppose. So how could I get from here to here? Well, I could go directly via E twice E, or I could go up to here and then one back. So I could do E3 back with F. And finally, I could, did I miscount my dots? Well, yeah, I miscounted my dots. That should be symmetric. I could go up to here and then back. So doing this 4 times and then going 2 steps back. And in usual representation theory, what you would do now is taking the alternating sum of all these variants. In categorical level, you can't take an alternating sum because you don't have minuses. What you do is these are all triangulated categories, so we can form a complex. So I'll write this down. So Ti will be the complex that is going just directly there. So that would be E ki minus 1 times I ran into my diagram. Or I can go one further, ki minus ki minus 1 plus 1, and then go 1 back. And the map here, remember, E and F's are adjoined. So I'll have an adjunction map from here to here. And then I can continue the diagram. And the Ti will be the convolution of that complex. And the theorem for this by, I guess, Cautis and Kamnitzer these Ti satisfy the braid group relations. In other words, they give an action of the affine braid group, in our case, on that sum of all the categories. notice that specifically, if we look at the category K111, sort of the middle category, then if I switch two indexes here, nothing changes. So I'll have a braid group action on this thing. And specifically, if we take the example of the nilpotent cone, then I get a braid group action on the bounded derived category of the Springer resolution. So remember, the Springer resolution can be written as something like that. I had an example earlier. And this recovers that mysterious braid group action, or mysterious maybe, under quotation marks, that I had in the definition at the very beginning. So what this theory does for us is it at least gives us some reason where this braid group action comes from.
Technically, the TIs just generate the action of the usual braid group. If the affine braid group, we need something by language.
Yeah, I'm a bit dodgy here. But if I already have the E nodes, then I can write it like this too, I think. If I already, I wrote originally as in Katsmoody presentation. So I've been a bit, I haven't quite followed the way you actually prove things. I've simplified a bit. So if you already have E nodes, E1, and so on, then I think that is correct on the nose.
So for the nilpotent cone, it's in type A that you recover
This is, I'm only talking about type A now. Simply because there we worked out all the combinatorics.
Wait, you can recover the same affine braid group action, you can put it as part of
I think so the braid group action you get for anything.
Can you extend that as to an action of an affine Lie algebra outside type A?
No.
I mean, there's no natural way.
No, only type A.
Yeah. So
Well, in other types, you'd expect one of these folding constructions. Co-ideal.
So it's something else.
yeah, so the affineness, I guess, is something specific to this. And I'm sweeping things under the rug. It's not trivial to define the GLN hat action to start with. But it can be done. And it's usually done via loop presentation. Okay, I hope, this was a very quick and very high-level overview. But I hope you got something of an idea what is happening. So let's tie this back to the original question of trying to get some T-structures. So actually doing this thing we said in the title, obtaining T-structures. And to specify, I'll take I'll fix n smaller or equal to n. Sorry. Fix this thing and assume k of k is 0 unless the sum of the ki is equal to n and all ki are positive. So the examples that we had, if you don't have this, you don't get if you have something negative, you don't get a reasonable flag. If you're switching between different sums, then there's no ei and fi that gets you between those anyway, so they're independent. So we can assume this without much loss of generality. And this is because we are interested in these specific examples. So let me give you a theorem. Suppose, so in that example that I gave you, you saw that the highest weight category, so the category K, N, and then a bunch of zeros, these were always much easier to deal with than the more central category. So this was just, say, the actual Lie group instead of some crazy Grothendieck-Springer resolution. So just an affine space, so that's much easier. So assume we have a T structure on here. Here's a T structure. And what we want to get from this is we want a T structure on all the other categories. So the conclusion should be there exists a unique T structure on all the other guys, on all the KK, such that all the functors EI and Fi, including E0 and F0, are T exact. Yeah, so that's a very reasonable condition. This is the only functors we really have to play with. We want them to be exact. So if one wants to formulate a theorem like this, what kind of condition would one have to fill in? Well, first of all, let's just do something stupid. Let's start at this category, and let's just do the functor E1 once, then the functor E2, and so up until En minus 1, and then E0. So what we do, E1 shifts 1 over here, so we have N minus 1, 1. Then we shift the 1 further down until we come back to N. So that will be an end of functor of that category. And obviously, if all the EIs have to be exact, that thing at least has to be exact. So that's the simplest thing that we can write down that has something to do with this category. So this has to be exact. And more specifically, it has to be exact for all powers and for the corresponding things with Fs too. And secondly, if you think about the categories with the non-fat y's, then this thing was just a point, while inside you have much larger varieties. Clearly from a point you can't deduce much, so this thing needs to be big enough in some sense. That was also what I said at the beginning. We want to look at G tilde instead of N tilde. And categorically this means that this outermost category, highest weight category, should weakly generates the innermost category, okay, 1, 1, 1, under the action. So what I mean by this is you start out here, apply a bunch of E's and F's until you come to this, and under all those functors you should categorically generate this middle category. So the image should be big enough that you can say something about the middle category. Otherwise, you'll never get something unique because you have a bunch of rest of the category where you can do anything essentially. But under these two very minimal conditions, you do get a unique T structure on all other categories. And moreover, to tie this back to this original thing here, moreover, we had a defined breakgroup action, so the submonoid, the action of the submonoid generated by T0, T1, and so on, is right exact. So we get something that fulfills this weird condition, automatically fulfills this weird condition that we had at the very beginning for the exotic T structure. So maybe to give you an example to tie this all back into the original thing we started from. So what you can do is, these two conditions are very easy to check. Conditions are satisfied for any perverse coherent T structure. So in particular, for example, the standard T structure on dB fat y and 0, 0, potentially equivariant. So in that case, these functors will just be tensoring with some vector bundle that is always exact. And it turns out these categories are exactly, so these spaces are exactly big enough that things are generated. So if you start with the middle perverse T structure here, so start with, say, lower middle perverse T structure, this T structure on, in the specific case of the just dB of G equivariant, then we get a T structure on dB of G tilde, and then we can restrict the T structure to dB of N tilde, or everything equivariant. And what one gets back is exactly the exotic T structure of Bezrukavnikov that we got started out as motivation. And similar, for more general things, we get again a T structure on 1, 1, 1, 1 something. We can restrict this to the non-fat y 1, 1, 1, 1. And then there's a companion theorem that we can get the canonic T structure on all the other y 1, 1, 1s. So for example, or the other non-fat y's. So for example, these convolution varieties that we had earlier. So we will get canonic T structures on all of these things.
Do you have an example of non-trivial T structure on dB of G?
So if I take the trivial T structure here,
Yes, because there is an infinite number of orbits if you don't take the nilpotent cone. So
yes.
is there an example of non-trivial T structure?
So if I take, I don't know if I get something interesting if I take the trivial T structure on this. But if I take it non-equivariantly and start the trivial T structure, then on here I get the representation-theoretic perverse exotic T structure of Bezrukavnikov and Mirkovic.
And on T of G, is there some non-trivial?
Yes, there is.
I mean,
by Filmmaker, Bezrukavnikov, you can still relate to. I mean, it's the deformed version of Symplectic. There you have.
You transport.
Yeah, you can transport with that.
But you mentioned this lower middle perverse T structure.
yeah, this is just because, so if I want something on here, I'm actually only interested in the nilpotent cone in here. So I put some T structure on that, and then I have to extend it somehow to the rest, because I want the rest. I need the rest somehow. And the way is to do the lower middle perverse T structure. So the orbits here are not even dimensional, or so I take, instead of something in the middle, so half dimensional, I take bracket down, half dimensional, so round it down or something. So there's just a canonical way, or I can do the upper one, doesn't really matter. So in here, what I'm really interested in is dB n, or I guess dB G with support on n. That's what I'm actually interested in. I have not much time left. What I want to say now is just give, so the proof has two parts. It has a theorem that is I find very useful for a general statement, so that I want to show you. And then the rest is combinatorics. So let me give you the sort of the core of the idea of proof. And that is the following. Essentially, it's a corollary of a theorem of Polishuk. And that goes like this. Suppose phi from dB of x to dB of y is some Fourier functor. Phi is conservative. And finally, dB of y has a T structure. Such that if I go from dB of y by the left adjoint back to dB of x, and then go back to dB of y, that is right exact. Then the T structure uniquely lifts. So then there exists a unique T structure on dB of x such that phi is exact. So the idea of the proof of this theorem that I now raised is you use this theorem over and over again. The weakly generating gives you the conservativeness, and then do a lot of combinatorics to check that you don't run into any contradictions, and that one simple condition is enough that you can't have any contradictions. So sort of what I want you to take away from this talk is maybe not that exact result that might be interesting to some of you, might not be interesting to others, but when you want to construct T structures, one way to do is put everything into some bigger diagram where you have more spaces to work with, hopefully something easier somewhere on the edges, and then try to do some argument with a theorem like this and combinatorics to inductively go on into more complicated spaces. Okay, thank you.